A word on buffer capacity. Buffer capacity is the measure of the ability of a buffer to minimize pH changes with the addition of an acid or a base. That buffer capacity becomes greater when we have larger concentrations of a base and its conjugate acid. And that would certainly make sense. As we've learned, what changes when we add either a strong acid or a strong base is simply the concentrations of the base and its conjugate acid. When these concentrations are higher, the change in concentration, the same amount of change in concentration, is going to have a smaller impact on this ratio. This is easiest to see if we work through a few calculations. Let's calculate the pH change of adding a strong acid to a buffer. In this case, it's an acetate buffer, and the concentration is 0.1 molar of each the acid and its conjugate base. This is a buffer. We're going to be using the Henderson-Hasselbalch equation to calculate our pH. So we're going to have to calculate our new concentrations of our base and our acid after this amount of acid is added. We know the initial concentrations, but we want to calculate these concentrations after the added acid has been absorbed. To do that, we first need to know the initial amounts of our weak acid and its conjugate base, and we do that by multiplying our concentration times our volume, and we get 0.1 mole of each of these components. As in previous problems, we're going to construct our BCA table, as we have initially 0.1 moles of each our weak acid and its conjugate base, and we're adding 0.02 moles of our strong acid. Now these are the amounts of everything before the reaction with the buffer. We add the H3O plus, it reacts with the buffer, and there's enough of the base component to consume all of our added acid, but we also lose some of our base, and we gain some amount of that same amount of our conjugate acid. So now our amounts are 0.08 moles of our base and 0.12 moles of our conjugate acid. We put those values into the Henderson-Hasselbalch equation. We add our values. So pKa is a negative log of the Ka. And then we take the log of the ratio of the moles. So remember, we're in the same beaker, so we can do the ratio of the moles rather than taking the time to calculate the individual concentrations, because the ratio of the moles is going to be the same as the ratio of the molarity. When we put these numbers into our calculator, we get 4.74474, and this is going to be a negative 0.176. So the pH of our new solution is 4.5686. And with 2 sig figs, 4.57. You may remember the calculations that we have previously done, in that if we have 1 liter of an acetate buffer and it had higher concentrations, we added the same amount of an acid, we had a much smaller change in pH. This current solution has a smaller buffer capacity. Previously, we calculated the delta pH for adding 0.02 moles of HCl to a liter of buffer, the difference being the concentrations of the weak acid and the conjugate base were much larger, 0.5. We had higher concentrations here, so even though we have the same delta for this buffer solution, the delta pH is much higher because the ratio is changed by a greater amount. Now we'll take it one step further, and that we have even lower concentrations of the weak acid and its conjugate base, and we're going to expect that the delta pH of adding 0.02 moles of our strong acid is going to be even larger than it was for this case. We go through the calculation the same way. We calculate the initial moles of our weak acid and its conjugate base, because we're going to use these values to plug into Henderson-Hasselbalch. Then we need to determine the concentration of each after that has reacted with the added H+. So we have our BCA table. We have 0.02 moles of the added H3O+, and initially we have 0.05 moles of each of the buffer components. We still have enough to consume all of our added acid. Zero, 7. And we can plug these values into the Henderson-Hasselbalch equation. And when we chunk out these values, we will see that there is a much larger change in pH. We have a pH after adding the H3O+ of 4.38. So what we see is that as the concentration of our buffer components decreases, we have larger values of delta pH because the buffer capacity is weaker when these concentrations are lower.